we have Mario Kummer telling us about spaces of Lorentzian polynomials.
Thank you very much for the invitation and for letting me speak here. Apologies to those that have already attended the talk by me under this title. It will be similar in the first half, but in the second half, see something new. So this is a joint work with three of the organizers, Matt Baker, Huh and Oliver Lorscheid. And although I believe many people in the audience know Lorentzian polynomials, I will first define them. There are many ways of defining Lorentzian polynomials, and I choose the say the historical approach. So I first define what a stable polynomial is. So F, multivariate polynomial with real coefficients, say non-negative coefficients. It's not necessary to require this, but later we will be only interested in polynomials up to some scalar factor, so this doesn't make a difference. So what is the this such polynomial is called stable if it does not vanish whenever we plug in for every variable complex number from the upper half. Okay, so actually, I mean, originally this concept comes from control theory, but actually combinatorists became also interested in this. And the reason is that by Dewey, Oxley, Sokal, and Wagner, which says that if you have a homogeneous multi-affine stable polynomial, then the support is the set of bases of the matrix. Homogeneous. So let me be very precise. So F is stable, homogeneous, and multi-affine. This means we can write F as follows. F has some degree D, then we sum up over all D element subsets of the set 1 up to n, some coefficient pi, then the monomial corresponding to I. So this means that F is homogeneous and multi-affine. And then, as I said, then those subsets for which this pi is non-zero, they form the set of bases of a matroid. So and in this talk, I will identify a matroid with the set of its bases. So whenever I say a matroid, I actually mean collection of sets that satisfy the basis exchange axiom. So why is this interesting? So this makes it possible to study at least some matroids, namely those that arise in this way through methods that, like continuous methods, can apply to this stable polynomials. Look at properties of the stable polynomials deduced from these statements on the matroid. Unfortunately, this it is not true that every matroid arises in this way. So these methods are somehow limited, and this is why people have come up with a more general notion of polynomials, which captures more matroids. So these are Lorentzian polynomials. So let me maybe write like put this index D for the vector space of all polynomials that are homogeneous of degree D. So F the affine homogeneous of degree D and non-negative coefficients. Is Lorentzian. We require two things. So we want that the support of F so this is the support of the polynomial or the subsets where the coefficient is non-zero. The support should be a matroid. And it's not necessarily stable itself, but all derivatives, so for all subsets of cardinality d minus 2, the partial derivative, partial derivatives in all the coordinate directions from this subset of F would be stable. These polynomials turn out to be the right ones for carrying out this idea of using this continuous geometry of polynomials methods to matroids. And this was introduced by Brändén and Huh, and also by Anari, Uweisgaran, and Cynthia, who just arrived, although under another. I said that these are a generalization of stable polynomials. This is actually true. So every stable polynomial is a Lorentzian polynomial. So we have to check these two things. So the first condition is just this theorem down. And for the second condition, we need to check that if polynomial is stable, then also all the partial derivatives in coordinate directions are stable. And this more or less follows from the fact that if you have a univariate polynomial and look at the zeros in the complex plane, then the derivative will have zeros in the convex hull of these zeros of the original polynomial. Like this, you can prove that. If you don't have any zeros in the upper half plane, then the derivatives will also have zeros in the upper half.
Right, that was how we should think about stable, or how we should think about Lorentzian.
What do you mean by think about Lorentzian? This is this is what I just explained is why are stable polynomials Lorentzian?
Oh,
Because the derivative, like so yeah, I want to prove stable polynomials are Lorentzian. So I need to verify these two conditions. This is the theorem that I wrote down. And then I need to prove that if you have a stable polynomial, then these partial derivatives are stable. And this can be done using this argument that I explained.
okay.
And what about quadratic forms? Stable. Sorry.
Sorry, but yeah, okay. I mean, for quadratic for quadratic polynomials, there's a nice characterization of stable polynomials. Namely, you look at the Hessian, and this should have exactly one positive eigenvalue.
Can you say a word about which matrix do and don't arise as supports of stable polynomials?
I will say something about this, but there's no characteristic. So yeah, maybe let's. I will say something. So we want to think. We want to now look. Given given the matroid, we want to look at the space of all Lorentzian or stable polynomials whose support is this matroid, and like we think of it as some kind of realization spaces, similar to the things Lucas talked about yesterday. So
Can you fix the boards before we move on? Put it down.
is the no visible?
Yes. Both is the forecast.
Okay, so M be a matroid of rank D on n elements, and then we look at all stable polynomials having this matroid as support and same for Lorentzian polynomials. And yeah, as I said, we want to think about this as like some kind of realization spaces, right? If you have a can write a matroid as the support of a stable polynomial, for example, then you have given a proof that this is actually a matroid. And we want to say something, for example, about the topology of these spaces. We will actually not look at these spaces, but the projective versions. So it follows from the definition that if you multiply a Lorentzian or stable polynomial by a positive scalar, it stays Lorentzian and stable. Look at the projective classes of non-zero Lorentzian stable. And now we can compare how these spaces relate to usual realization spaces, and this maybe gives a partial answer to the Rico's question. So if we, it's also one paper by Joey, Oaksley, Sokol, and Wagner, we have a map from the Grassmann cell of our matroid. So this small linear subspaces, points in the Grassmannian, whose Blücher coordinates, non-zero Blücher coordinates correspond to M, indexed by M. To all those points in the Grassmannian that realize our matroid, and there's a map to the space of stable polynomials. Which just you have the Blücher coordinates, then you take the absolute value squared and take these as your coefficients. So in particular, whenever your matroid is realizable over the complex numbers, there's a stable polynomial having it as support. I will also give an example for a matroid which does not arise in this way in a minute, but let me give another map now to the space of Lorentzian polynomials. So we look at the local Dressian of M, which is for all functions from the basis of M to the real numbers, which make this evaluated matroid. And since we would like to work projectively, we mod out the constant functions. And from this, there's a map to the space of Lorentzian polynomials given by with this map B, and then you pass to exponential coordinates. And these are the coefficients. So in particular, yeah. So
Change the base of the exponent. So that's e to the vi, but can you take something else?
again, if I can change the base, yes. Right, because the
X literally eight. Literally made like a to the something or e to the something.
I mean, because if V makes this a valued matroid, then every positive scalar multiple also does so.
Thank you.
Yeah, so this has the nice corollary, maybe here, that the space of Lorentzian polynomials is non-empty for every matroid.
The basis of a matrix.
Hmm?
It's not is from the basis of a matrix.
Yes, so I yeah. Always mean set of bases. Right, so because you can always, so the constant function is always makes it the evaluated matroid. So actually the basis generating polynomial of every matroid is Lorentzian. And this is in contrast to the situation for stable polynomials. Here it's not the case. So example by Brändén is you take the Fano plane, and there's no stable polynomial whose support is the Fano plane. This makes this really a better class of polynomials. Okay, so now examples. Maybe one more example. You draw maybe some.
Sorry, with the evaluation map, do you need to like allow native infinity or something?
Yeah. No, I don't want to allow infinity, because then, I mean, the support of such a valuation map would be those values where you don't have infinity. I mean, I really want that in the end, the support will be the matroid I started with. If I allow for minus infinity, then this will be 0 for some.
Wait, but I define my valuation to be minus infinity on like things that aren't in the bases of my matrix or something. I guess what is the sum of?
You can also define it on the set of all subsets of size
sorry.
D, and then say, okay, it's minus infinity for those that are not.
Does the min-max convention matter here?
Yes.
We are.
It's the next one. Yeah.
Yeah, I think so. Let me draw one picture and then pass on to the results. From the definition, I mean, I already told you that if F is stable or Lorentzian, then every scalar multiple is stable and Lorentzian. But in fact, we can even scale each variable separately by a positive scalar. This will not destroy this property, so this will also preserve these properties of Lorentzian and being stable. So I draw pictures modulo scaling the variables. Right, so this in this Grassmannian setup, this would correspond to you have your matrix and then you scale the columns. And in log coordinates. Because I want in the pictures I draw, I want to be the Dressian, I want to be a linear object and not some exponential one. So then the first interesting example that gives us a hint how the general situation like is the uniform matroid of rank 2 on 4 elements. Yes, many of you know how the Dressian looks like in this case. It's 3 rays. And you can look at the image of this map from the Grassmannian. These are these 3 segments. The real Grassmannian on the boundary, and then everything that is bounded by these is both stable and Lorentzian, and also in the image of the complex Grassmannian. Right, so modulo scaling, we see, okay, the space of Lorentzian polynomials is homeomorphic to a disk with 3 points from the boundary limit. Also in this case, it is full dimensional in the space of multi-affine polynomials, right? Because you have 6 bases and then you have 4 variables that you can scale. So you end up in a 2-dimensional space, and this is actually 2-dimensional. This is unfortunately not always the case that this is.
You also flipped convention.
Sorry?
You flipped convention.
No,
Don't worry, don't worry.
You mean from max to min or?
Don't worry.
Yeah, it's okay, since we don't have a sign with exponential, it's coherent.
Yeah.
So yeah, so in general, this space will not be full dimensional in the projective space of multi-affine polynomials of degree d in n variables. But there's a condition served by Brändén basically. So if you have a Lorentzian polynomial and then you take some d-2 element subset where d is the rank of your matroid, and then you take 4 elements that are not in your J. Then if one of the following things is 0, these are the 3 terms of the 3-term Blücher relations. If one of these terms is 0, then the other 2 must be 0. But I mean, so it's consistent with the fact that the Grassmannian maps here, right? So these are the 3 terms of the 3 terms Blücher equation. So if one term is 0, then the other ones must be the same up to sign, but because we take absolute value, the coefficients must be the same. And then it extends to not just to the image of this.
Can we tell people that in this set of Lorentzian polynomials are exactly log concave polynomials? Right.
In that setup, Lorentzian polynomials are exactly
The theorem like this becomes more cool. Like you start from this definition.
Okay. So in this case, Lorentzian polynomials are exactly log polynomials that are log concave on the positive.
Can you say what about when they are not the same?
The support is not multi-affine. Then there, yeah, for I think already for binary forms, right? Then you really need some derivative condition, some addition.
You
Then,
mean other derivatives, okay.
then you have to require that all derivatives are log concave in a positive way.
Sorry, what's the boundary of that blue amoeba that you drew with that?
The image of the
What equations describe the border?
It's the middle of a line.
Hmm?
Or you mean the general?
In this example of U2-4,
I can show it to you after the talk. It's a simple equation in this case. Okay, are there more questions? Okay, then, yeah, this is another reason why I choose to draw pictures in log coordinates, because so these conditions, so one is 0, the other ones are equal, is a binomial condition, but in log coordinates this is a linear condition. So this log coordinates, these conditions cut out a linear subspace, which contains the image of this space under the coordinate, the component-wise log. So log coordinates. This defines a linear subspace J M of R to D. And now I'm ready to state one of our main results. Namely, we can now So basically what happens here is true in every case if we are not live in this space. So here the space of Lorentzian polynomials is like modulo scaling is a disk, closed disk with 3 points removed, and the 3 points that we remove correspond exactly to the rays of the Dressian. This is what happens in general. So we have B is, since we work projectively, I mod out the space spanned by constant 1 vector, all ones vector. So if this is the closed unit form, then this is homeomorphic to this closed ball, but we take out from the boundary, we take out the intersection Dressian. This shows that our space is, for example, can be compactified to a ball. So manifold with boundary. We also know what the dimension is. It's dimension of this vector space. Okay, so let's draw some conclusions from this. So this can be used to let's look at the compactly supported Euler characteristic of the local Dressian. Yeah, so we can compute it as follows. So the Dressian consists of finite union of closed cones. So its compactly supported Euler characteristic can be computed from its intersection with the boundary of a ball, right? Because we have, if we know the intersection with the boundary of a ball, we know the entire Dressian. How do we do this? So for every point in this intersection, we replace by the open ray. So this open ray through this point. So this we need to multiply the Euler characteristic by -1 because we replace a point by copy something homeomorphic to R. And then there's also this open rays, and there's also the origin. This is like this, but then this is the Euler characteristic of the ball. Get was this compactly supported Euler characteristic satisfies inclusion exclusion for sufficiently nice spaces. We obtain that the Euler characteristics of these two spaces. And this, I think it's nice to know. If you're interested in this space, then you can compute the Euler characteristic from this space, because this is a polyhedral object, and here you can really compute the Euler characteristic by.
Yeah, is this theorem not two things we can't compute are related?
This we can, okay.
No, we can't compute the Euler characteristic of the Dressian. Well, for which matroids?
For some matroids we can.
U2 force.
Yeah.
there will be more, I mean, we will apply this to certain matroids and yeah, so yeah, for some matroids you can compute this. For example, I mean, this space, this VM, it can be very, very small dimension for some matroids. And for these matroids, you can also compute the. I mean, there's a.
We know what is the number for all binary matrices of any computation.
Yes, for example. And there's also this nice paper by Madeline Brandt and David Speyer, where they really compute this for several interesting matroids. And we can also compute it here. This, if you have this computed, then it's just this alternating sum of the f vector. So this
Computer programs to get there.
But is that how did you actually? Yeah. We can argue this.
okay. But you can, I mean, you can also, yeah, there's also the other direction is might be interesting. So let me, yeah, so here from this theorem, we get that this space of Lorentzian polynomials can be compactified to a ball, to a closed ball, but this is not, maybe not the compactification that one would first think of, right? We first pass to logarithmic coordinates and then do something like the projective closure. One could just take the closure of this thing in the projective space of all polynomials and ask for this, what is that compactification? So Peter Brändén has shown that for the uniform matroid, this naive compactification is a closed ball. And this gives the following corollary, which I don't know if it's interesting, but let me write it down. So if you, so you also showed that this space is actually the disjoint union of all PLM, where M goes over all matroids of rank D on n elements. And so the sum must be 1 because it's a closed ball. Then by this, it's I don't know. I found it nice. Whole level 2. So for uniform matroids, this is a closed ball. So the question that Peter asked is this maybe a closed ball all the time? Also ask this for stable polynomials.
Or is this over matroids with the same VMs?
Sorry,
How did we leave VM there?
how do we leave?
I thought you were somehow, maybe you're not.
We are not leaving, we are not, okay, so this is in log coordinates. This is in the original coordinates. So this, in the original coordinates, if you go like along this ray, there will be a limit point.
VDN means.
It's uniform matrix.
For matrix, sorry.
It's just a notation UDN.
It looks like a V.
I'm sorry. Yeah, this happens. This happens. Okay, so if these things would be balls, then the Euler characteristic would be 1. So maybe we compute the Euler characteristic of these things for our favorite interesting matroids using the decomposition into disjoint strata, also this. So we start with an example. So if M is binary, June mentions this example. So then M is binary, then this this vector space Vm modulo scaling is just 1 point. Also the Dressian is then, I mean, up to linearity, just 1 point, and then we can really do computations. Draw the picture. Yeah, and then so this means the closure is so this point. No, I mean now there's something happening. This point is I draw pictures modulo scaling, so this is actually an orbit under the rescaling action of all the variables. So it's an orbit. So this is an orbit closure. And orbits in this space are in bijection to faces of the matroid polytope. And actually, so these orbits, they are not just in bijection to the faces of its matroid polytopes, they are also homeomorphic to the relative interior of the corresponding cell, because the matroid polytope has Euler characteristic 1. This is also true for the space. I think we also believe that it's actually homeomorphic to a ball, but we not carried out the details.
Could you explain why this VM is a point?
You can?
They know about foundations.
Oh, from foundation.
One way of thinking about it is that binary matrices are the ones that don't contain U to 4. That means the matrix polytope has no octahedra inside.
I see.
And to create subdivisions, you really need to subdivide octahedra.
That shows that the Dressian is only a point. And then there's this stronger statement that also the foundation is a point, which implies that that this one is just a point. But I mean, why the foundation is a point? Is this something one can explain in one sentence? Or is it...
Again, because it has no U2 forms.
Okay.
It's generated by U2 forms. You could say that all cross ratios are degenerate when equal to 1.
I see. Okay.
There's a question.
That's a question? Yep.
What is acting here?
Yes. So you can scale every variable by a positive scale. The remaining time, I want to use some more examples, 2 more examples, namely. So in this case, it's probably a positive answer to this question, but I want to show 2 matroids that are, this is not a polynomial, this is not. So the first matroid is the Betsy-Ross matroid. This is a rank 3 matroid on 11 elements. Here, this space is one-dimensional because the foundation is the golden ratio partial field. And here the picture looks like this. So this is one-dimensional, so I'm drawing something on the line. And we have two boundary points, so the space of Lorentzian polynomials will be a closed interval. And this means we are not removing anything from the boundary. So this means that the Dressian can only be a point. This is the Dressian. The Lorentzian polynomials, and the blue points, the boundary points, they are actually the stable polynomials. And they're also the image of the Grassmannian over the reals or over complex numbers. So I think there's several interesting things happening in this example. So one is that this is the space of stable polynomials is disconnected. So it's the only example I know where this happens. And also the Dressian doesn't span the entire space. The M is also it's the only example I know that is.
Can you read the blue?
SM, so stable polynomial, projectivized stable polynomials, and image of the Grassmannian over the reals of M and complex numbers.
Can you give some intuition for how we know that there are no stable polynomials inside that interval? Why it's just the endpoints?
Okay, I can give a so this so there's an easy argument why it's disconnected, why it doesn't contain the origin. This is because if it was, then this basis generating polynomial would be stable, and then this thing has a minor called F7 minus minus, further relaxation of the Fano plane, and this is known to have the property that it's base generating polynomial is not stable. So this shows that it's at least not connected. Then for really proving that this is that these are only the boundary points, I do not have a good explanation. It's really like a calculation. Not too terrible, but.
If you don't mind a question about the name, there are just two people whose surnames happen to be Betsy and Ross. No connection.
No, Betsy Ross like
Like the flag.
Yeah.
Well, okay, no.
Yeah.
It has some representation that looks like a star. So during that project, I learned that about American history. Because okay, more comments or? Yeah. Okay, so this, I mean, this is because this ESM is disconnected. This is a good candidate for a negative answer to this question. That we need to take the closure and then see what happens. Unfortunately, the closure of PSM is actually connected. So it's just not just such an easy argument, but we can compute the this Euler characteristic. right? Because so these are 2 points, so actually 2 orbits. So we are looking at 2 orbit closures. In this example, I have already explained how orbit closures look like. So this look at the strata correspond to faces of matroid polytope. So all we have to do is to check for which faces of the matroid polytope of this matroid the 2 strata of these 2 points are the same and for which they are. And this is something that a computer can actually do. So this matroid polytope is quite large and I think it has 20,000 faces, but this is something that the computer can do, and this resulting Euler characteristic is 17, not 1. So this is an example for the for this question, and I also want to present example where the space of Lorentzian polynomials is not a ball, and this is one of the matroids that we have seen in Luca's talk. So for n at least 4, the elliptic matroid En is the rank 3 matroid on n elements whose non-bases are the following. So all 3 element subsets I, j, k, such that n divides the sum I plus j plus k. And the name elliptic matroid is, as we have seen yesterday, this matroid can be represented as follows over the real or complex numbers by take a elliptic curve in the plane, and you take a point whose order is a torsion point, whose order is n, and then you take the group generated by this point, and these points in the group, they represent this matrix. Because sum of 3 points, 3 points lie on a line if they sum up to 0. And things start to get interesting for n equals 11. And equal to t11, then in this case this is 4-dimensional. I cannot draw anything 4-dimensional, but I can draw the projection to some plane, and this is valid in this point because here the Dressian is just 5 rays. The reduced Waterloo scale. And so the Lorentzian polynomials are somehow something 4-dimensional containing these 5 rays. Now the interesting thing that happens in this case is there is some so that for 2 rays you can look at the closure of the 2 rays, or the in the usual coordinates, they will have the closures will have something in common which does not come from, which is not in the orbit closure of the origin. So this somehow means that there's really a loop in this closure space. It's the also the smallest or the only matroid that I know for which this happens, although we believe that for prime numbers larger than 11, this should also happen. And yeah, because the situation is so simple in this case, so we really have Dressian only some rays, can compute the compactly supported Euler characteristic in this case. So what, yeah, any guesses what it could be? It's not 1.
6.
Two ones. It's 11. I don't know. I don't think it's a coincidence, but we have no idea. Okay, yeah. So in particular, it's not a ball, and we also answered the other question. And yeah, that's what I wanted to tell you. Thanks.
Question for Arne? So the identification of PLM with an open-dense subset of a ball, what's the choice of coordinates that gives that identification?
The log of the coefficients.
I see. So is it a fair takeaway that for this type of question, we should think in log coordinates?
I think so.
So all the Euler characteristics you wrote down were positive. Is that true? You know?
I mean, so I know 2 numbers that are the Euler characteristic of such a space, and one of them is 1 and the other one is 11. This is really the only example we have that this is non-zero. I don't dare to make some.
What is special about this matrix that you're able to compute?
Say again?
What is special about this matrix that you are able to compute?
That we are able to compute this number. The special thing is that the Dressian is only one-dimensional.
I see.
Then it's really computations.
You know if Stable and Lorentzian agree for that matroid?
I do not know.
What was the question?
They agree. Stable and
I do not know. There are certainly stable polynomials having this matroid, realizing this matroid representation, but I don't know. It's a good question. Should check.
Has anybody studied the topology of hypersurfaces of Lorentzian polynomials?
I don't think so.
It seems like you have some kind of patchworking hanging around. Patchworking polynomials that are related to.
Okay, sorry. So, okay, I think I understood. We look at the zero set of a Lorentzian polynomial. You want to know what it is. Yeah, I think that's. I think the topology of the zero set is not the right thing to look at for Lorentzian polynomials. So, for example, there's this. So I guess you know better than I do. So this is the zero set of a degree 6 polynomial, and in the proximity of this polynomial, every topological type of a zero set of and after if you do a linear change of coordinates, this becomes Lorentzian, strictly Lorentzian, so that small perturbations also. Then you
get everything.
You can get everything. I don't know if this happens in any degree and dimension, but I believe that there's no real restriction.
It's not restricted to like stable polynomials.
Exactly, yeah.
when he defined this Lorentzian, can he relax the condition like multiplying or homogeneous?
I mean, if it's not, yes. So then you have to replace this by M convex set.
He also asked about homogeneous, but that's an open problem, right? If you can relax the homogeneous.
If you can relax the homogeneous. No, that's not clear what the concept.
Yeah, we can, but there are no theorems.
So in that example, M is a matroid with a weak half-plane property, but not with a half-plane property.
Exactly. Yes.
And do you expect all such matroids, like all such stable polynomials, to appear as boundaries? So PLM. Or is it just a coincidence?
So yeah, I don't know. It's I think it's at least plausible. So what is true is that the image, the image of this map from the Grassmannian, which is always contained in the set of stable polynomials, if your matroid does not have if your matroid has a U25 minor, then you will end up on the boundary. So this somehow constructs, this constructs you some stable polynomials on the boundary of the space of Lorentzian polynomials. I don't know, but this is something that one might be able to check in some examples. Okay, no, the answer is no. Some example occurred to me that the F7 minus the non-Fano plane has the weak half-plane property, but not the half-plane property. Okay, no, but then it's also on the boundary. Okay, no, sorry, take it. Might be.
If there are no further questions, let's thank Mario again.